So in the book, in chapter 2, where we work on 2-point boundary value problems, they quickly acknowledge that we're not able to attack all different kinds of boundary value problems at once because that's quite a big box of different types of problems. So when they present a finite difference method for boundary value problems, they start out with looking at one specific type of boundary value problem in the book. On page 46, formula 26, they present to us what is called a second order linear inhomogeneous differential equation, which with two known values of the solution, namely that y of 0 equals alpha and y of L equals beta, constitutes one type of boundary value problem, which is, well, apparently common enough such that they would think this is a good example to use. I'm sorry, it's not formula 26, it's formula 24. So just before I start talking about this thing here, let's brush up on some differential equation terminology. So what does it mean that we have a second order differential equation? A differential equation is of second order when the solution is derived twice. So this is the reason why we have a second order differential equation. If we had another differential equation where the third derivative of y was also included, then we would call it a third order differential equation. So the order of a differential equation depends on how many times y has been differentiated in the expression for the differential equation. Okay, so why do I say that this is a linear differential equation? Well, the reason why it is linear is because y and the derivatives of y, so namely y, the first derivative, and the second derivative, are all in a linear combination in this differential equation. So what would not be a linear differential equation? That would be something along the lines of, for example, a differential equation that looks like this, where the second derivative of y is, for example, minus e to the y. Because then y is not contained in merely a linear combination. So when we say y and its derivatives are expressed in a linear form, then it's when they're added together with some functions multiplied in the front. So for example, here it's e to the y, which is not a linear function, and hence this differential equation, which is also called Bratu's equation if you've read the book, this is not a linear differential equation. But yes, in this part of the book, we work with a second order linear differential equation, which is also inhomogeneous. So what does it mean that it's inhomogeneous? Well, inhomogeneous means that when I take all the terms where y is contained or where derivatives of y are contained and I move them all to one side of the equation, then I am left with 0 on the, wait, did I say inhomogeneous or homogeneous? If I am left with 0 on this side, then it is a homogeneous differential equation. If I am left with some kind of expression on this side, then it is called an inhomogeneous differential equation. So what we have here is a second order linear inhomogeneous differential equation. So what is the reason why I wanted to spend some time and talk with you guys about the classification of different types of differential equations? Well, mainly it's because that if someday in the future you meet a differential equation and you're looking at it, then it could be quite nice if you could just Google something and learn more about it. And in order to be able to do that, you need to be able to classify whatever kind of differential equation you meet into, well, just the typical types of differential equations. Okay, so let's continue. This boundary value problem is what we study in most of chapter 2. And you can see that I've used some different colors here. And the reason why I did that is because we need to be very certain of what we know and what we don't know in this differential equation. So P of x, Q of x, f of x, the interval that y is defined on, namely 0 to L, and the value of y in the interval endpoints, these are all known quantities. So an example of a second order linear homogeneous differential equation would, for example, be an equation that looks like this, where the second derivative of y plus, let's just say, x squared multiplied by the first derivative of y plus cosine of x multiplied by y is equal to minus 12e to the x. For x belonging in the interval 0 to 2 pi, where y of 0 is equal to 1 and y of 2 pi is equal to, let's just say 42. Then in this case, based on the differential equation, we're able to read off the different values of these coefficient quantities p, q, f, alpha, L, beta. So let's just, for getting started, what is p of x? Well, p of x in this case is x squared, because that's what we have standing in front of the derivative of y. And q of x is equal to cosine of x, because that's what we have in front of y. And f of x is what we have left when we have moved all the expressions containing y over to the other side. So f of x is equal to minus 12 multiplied by e to the x. And what is our L? Well, L is the left, no, not left endpoint. It is actually the right endpoint. I don't know why we call this L. It would be better to call it R. But anyways, L is equal to 2 pi, as we see here. And what we call alpha up here is in our case equal to 1. And beta is in our case equal to 42. Now, according to the book, there's a little piece of trivia that is very nice to know. In the book, page 46 to 47, is written that one can prove if P, Q, and F are continuous functions, and if Q of x is non-positive for all values between 0 and L, then the boundary value problem here has a unique solution. So if we know that this holds, then we know for sure that the boundary value problem has a unique solution. Now, do we know if that holds in this case? Well, yes, in this case it does not hold, because our q of x is cosine of x, which is positive from the value 0 to, well, let's see, at least it's positive from 0 to pi halves. So this thing with q of x being non-positive does not hold. So here we cannot be sure that this BVP has a unique solution, but it might. We just haven't proven that it does. Anyways, this was just a quick example so that you guys could become a bit more familiar with the boundary value problem that we work with in this chapter. And in the next video, we will talk about how to draw a grid and try to discretize this problem here, so that we can use our standard Taylor approach to try and construct a finite difference method to solve this problem numerically.